Hello and welcome to this manufacturing process technology part 2 module 44. We were discussing about the Tresca criteria, and we were also discussing about how to find out the principal stress, principal plane angle and the maximum shear stress angle. And in context of that, we had formulated several expressions where we found out that the principal plane will be at an angle. Let me just write this down here. Principal plane will be at an angle which is actually given by sine 2 theta p equals twice tau xy divided by root over 4 tau xi square plus sigma x minus sigma y whole square. And similarly, cos of twice theta p should be equal to sigma x minus sigma y divided by root over 4 tau xy square plus sigma x minus sigma y whole square. So having said that, let me just write this down properly. Cos twice theta p. So this is about the principal plane angle theta p. So theta p is the angle of the principal plane. Our learning was that further the sorry, there is a error in writing here. Okay, so our learning was here that at this particular plane, if we wanted to evaluate the maximum shear stress which is given by tau x1 y1 equals minus sigma x minus sigma y by 2 sine of 2 theta plus tau xy cos of 2 theta. This actually comes out to be, if we put this theta equal to theta p and try to find out, this actually comes out to be 0. Okay, so this comes out to be 0. So there is actually at the principal plane no shear stress, or the tau x1 y1 component at theta equal to theta p happens to be equal to 0. So we will use this criteria to sort of try to determine what is the maximum shear stress. We already know that the maximum shear stress is corresponding to, again, differentiating this del tau x1 y1 by del theta to be equal to 0, and from there we evaluate and we find out an expression or a condition, delta or sine of twice theta equals minus of sigma x minus sigma y by 2 divided by root over sigma x minus sigma y by 2 whole square plus tau xy square, and similarly cos of 2 theta as tau xy divided by root over sigma x minus sigma y by 2 square plus tau x square y. So if we put this values of sine 2 theta and cos 2 theta back into this expression here, which is actually meant for determining the maximum shear stress, so we can get the tau maximum, or let's say, just putting it this way, that the tau maximum here should be equal to the value of the tau corresponding to, if we just substitute these maximum conditions of theta. Okay, so that should be minus of sigma x minus sigma y by twice sine of theta, which is again minus of sigma x minus sigma y by 2. So this goes in bracket, divided by root over sigma x minus sigma y by 2 square plus tau square xy, and plus tau xy times of, again, tau xy divided by the same term here, sigma x minus sigma y by 2 square by tau square xy. So we can find out the tau max or the maximum shear stress to be equal to sigma x minus sigma y by 2 whole square plus tau xy square divided by root over sigma x minus sigma y by 2 square plus tau xy square, which is actually again under root of sigma x minus sigma y by 2 square plus tau xy square. So we already are aware that the tau xy at the principal plane corresponding to theta equal to theta b p should be equal to 0, and if we substitute this value back into the expression for tau max we get tau max equals sigma x minus sigma y by 2. So and this basically would be defined as the limiting value of the shear yield stress K. So supposing now in a material the shear yield stress is recorded as K, then obviously if tau max greater than or equal to K, the material will go in plastic flow. So material goes to plastic flow range or plastic flow region. Okay. So in this particular expression, therefore the tau max equals sigma x minus sigma y by 2 should be greater than or equal to K, and that's what is the Trescas criteria for plastic deformation or plastic flow. Trescas criteria. Now if we apply it to a specific forming problem, which is normally a plane strain kind of problem, let us look at this element of a material, let's say cubic element of a material, and we have various states of stresses in this particular element. Let's call this x, y and z. So there are the three principal stresses and associated also shear stresses corresponding to all these three directions. Let's call this sigma 1 direction, sigma 2 and sigma 3, and let's also call equivalent shear stress directions as well as this is this particular direction. So you have here tau 1 2, tau 1 3. Similarly there are two shear stresses in the principal plane 2, which is tau 2 1. In the sigma 2 direction is tau 2 1 and 2 3. So tau 2 1, tau 2 3, and similarly you have tau 3 1 and tau 3 2 in the z direction. So these are the total state of stresses, and if I may so recall that any forming processes, let's say for example if you are considering only the rolling process, the states of stress which really matter are the xz plane, if we look at it in that manner, and y typically the dimension is so big that there is hardly any formability or there is hardly any deformation or any let's say strains which are of considerable nature in the third y direction. So in all these cases we would really consider rather than the xy plane the xz plane, and so tau max in this case would actually happen to be sigma x minus sigma z by 2, okay, and along the principal direction, and so therefore this can be recorded in any event as sigma 1 minus sigma 3 by 2. Now if supposing if we wanted to consider the Trescas criteria, we should actually have the sigma minus sigma 1 minus sigma 3 component at least greater than equal to twice the shear yield stress of the material for the material to come in the plastic range. In a similar manner earlier, if you may recall, we had pointed out about how using the strain energy per unit volume or work of deformation concept we had arrived at the von Mises criteria. So in the von Mises criteria also we had a relationship between sigma x minus sigma y square plus sigma y minus sigma z square plus sigma z minus sigma x square to be greater than or equal to at least twice sigma y square, where sigma y is the uniaxial yield strength, okay. So this is actually capital Y, let us not confuse it with this y right here. So this is capital Y, uniaxial yield stress of the material, okay. And so if we wanted to follow the same principle here, where let us say generally in a forming process the sigma x becomes sigma 1, and let us say this is equal to some value k corresponding to which the material will come in plastic flow, or this is actually the you can say the constant material property, flow property, which is also the yield property of the material. And similarly we have sigma z equal to sigma 3 equal to minus k. Obviously, for example, if we consider a rolling process, let us suppose this guy will be compressive in nature, while this sigma 1 would be expansive for the material to get strained along the z and the x axis so that rolling can happen, okay. So having said that, now in the plane strain case we will not consider any kind of stress along the y direction, because obviously the dimension is too big for any marginal strain to be recorded in this particular direction. So we can call sigma y equal to sigma 2 in this particular case to be equal to 0, okay. So having said that, if I calculate the criteria corresponding to which the von Mises would actually yield, or the von Mises criteria would hold, or plastic flow would actually start happening, we substitute all these values back into this equation. Here we have k minus 0 square plus minus k square plus minus 2k square is greater than or equal to twice sigma yield stress square, or in other words 6k square is greater than or equal to twice sigma y square, which gives you an overall sort of condition that k should be at least equal to sigma y by root of 3 for plastic flow to happen. So that is what von Mises criteria says, that the maximum value of k that should be at least equal to the yield value divided by root of 3 for the plastic flow to happen. In the Trescas criteria, or the Trescas case, if we apply the same formulation, we have this shear so in the plane strain case you simply can have that one of these sigma 1s are equal to, let us say, the uniaxial stress sigma y, okay, and you could actually have this sigma 2 to be equal to 0 in uniaxial loading, and you could have the k to be equal to sigma y by 2, okay, for the plastic flow to happen. So the criterias are completely different in terms of what would be that critical limit beyond which the plastic flow would take place, and von Mises criteria is slightly better than the Tresca criteria, it is more accurate. And so we will basically now apply these criteria, both these criteria, to real forming processes like rolling or forging processes, and try to see how plastic flow can be initiated and what is going to be the mechanics of such process. So let us now apply some of these yield criteria to real processes, real metal forming processes. And in context of that, the first process that I will start with is rolling process, okay. So we will just do some modeling related to rolling, try to find out what are the kind of forces which are involved in doing rolling process, and we can also probably talk about some mechanics which is involved for obtaining the pressures which are there at the rolls, or for instance the driving torque which is needed for driving the rolls so that rolling may happen. So all these different models can be represented here. So the basic objective of the analysis here is to really determine number one, the roll separating force, number two, the torque and power required to drive the rolls, and maybe the power loss that is there in the bearings. We would try to make some assumptions and this is normally done for simplifying the analysis or simplifying the real situation. Actually the situation would be quite different, but at least from first principles can we arrive at a model where we can estimate all these things related, or all these parameters related to the rolling process is going to be the scope of the teaching here in this particular lecture. So we assume that the rolls are straight, and rigid in nature, the cylindrical rolls. Okay. We also assume in our analysis that the width of the strip is much larger than the thickness, and we further assume that no significant widening would happen on the width side because of the rolling process. We just wanted to so basically we are just converting this or simplifying this into a plane strain problem, and because now it is only about the change in the thickness vis-a-vis the change in the length. The width is so large that it is sort of neglected quite a bit in all the operations related to the rolling process. Further, it is important to assume the coefficient of friction to be low, and for simplicity's sake, although obviously friction would depend on the temperature to some extent, but in this case we assume the friction to be constant. Okay, so we assume the coefficient of friction mu between the roll surface and the strip surface to be low and constant. Further, we assume that the yield stress of the material remains constant for the entire operation. We are not having a changed yield stress because of strain hardening or other issues, and we would just like to have average constant value of yield stress of the material. Now these are presumptions which actually in the reality may have to be significantly different because of the fact that there is going to be a strain hardening effect, and there is going to be a change in the yield criteria, sorry, not the criteria but the ultimate yield strength of the material because of strain hardening and so on and so forth. But these we simply assume to be negligible in our model, And with these assumptions, if we start the model, let me just draw how this rolling operation is happening, or as a matter of fact, what are the different kind of stresses which are there on the material element which is being foreseen here. So let us assume that we have a metal strip which is being changed cross sectionally by two set of rolls. And it changes its thickness of the material. This is the sort of distance between both the rolls. Let me just draw it a little more appropriately. So that there is a change in the thickness of the material emanating from this particular portion, and I would assume certain parameters here. Let's say the final thickness of the sheet that is coming out of the rolls is Tf. The initial thickness which was there right at the beginning of the process is Ti. Obviously there is going to be a velocity at which this sheet is being fed. Let's consider that velocity to be Vi. This is Ti. Let's write it down in a more appropriate manner. Velocity here is Vi. We have a final velocity somewhere here, Vf. There is a velocity of the rolls. Both rolls are moving at a velocity v, and obviously the two centers around which this roll is moving are represented by O1 and O2. So this right here, let me just pull this term out here and write it slightly over here, average. So this is O1 and this is O2. Similarly, we also have an angle which is defined by the start of the rolling process all the way to the center here, and specifically we are talking about this angle right here, which is actually theta. So let me just write this out here as angle theta. Okay. Similarly, we estimate, or we just write down the radius of the rolls here as r, and further we assume that there is a small strip where we want to really obtain the mechanics of all the forces, or the interplay between all the forces in this rolling process. I am representing this strip with a shaded region, and let's suppose there is an angle d theta from the center of the rolls over which this strip is being considered. So I would like to consider the angle here between the dimensions of the shaded strip, and I would consider this angle as d theta. Okay. Further, I will consider the angle theta to be equal to the initial angle theta I. Okay. because that's what the initial angle is at the instance of time t equal to 0 of the rolling process. We are assuming the process to be in a manner that rolling is already happening, and we would look into such a formulated region right here and try to investigate the balance of forces in this particular region. Obviously, we are having stresses in this particular metal roll in both these directions. This is the reaction stress sigma xi, I can call, which is trying to push the thicker material away from the rolls in the reverse direction, whereas this is the forward stress sigma fi, which is trying to pull the material into the thinner zone. Okay, so they are opposite to each other, and obviously the balance is being played by the frictional force, which is actually frictional force of the roll, which creates a situation which drives the thicker sheet forward, okay, and therefore subjects it to stresses and strains, which changes the sectional area of the sheet. So having said that, now we have in general written down, so I will just write down all the geometric details that I have planned in this figure. Let's call this figure 1. Okay, so the first thing I have written down here is that the initial thickness of the strip is going to be Ti. The final thickness which it gets rolled into of the strip is going to be Tf. We assume equal roll radii of capital R and similar circumferential velocity to be equal to capital V. Further, the origin of the coordinate system, so let me just mark all these geometric details by different stars. So we assume also the origin of the coordinate system at the midpoint of the line joining centers O1 and O2. So somewhere around here, maybe at the very middle, if I were to extend this middle, so this is the point O. So origin of the xy coordinate system, which would be used for doing our analysis, force analysis, coordinate system is at the middle of O1, O2. And we call this O, right? So this is the origin O. In our particular analysis, we will consider the width of the strip to be unity, equal to 1, and why we do that is that because obviously we don't have any influence in the direction outside the page, okay, so therefore because it's a plane strain case, and so therefore it is, per unit width we can actually report whatever we are doing on this so-called XZ plane. And obviously the entry and exit velocities of the strip, which are taken to be Vi and Vf. So I will write this down here further. The entry and exit velocities taken as Vi and Vf respectively. And in actual practice, I would like to assume this in a manner that the Vi is obviously lesser than Vf. We assume that V is really the roll velocity, which is somewhere along the point of contact of the sheet metal with respect to the roll. You have to understand that the roll at some point of time is in direct proximity or in direct touch and kind of flows the material at the same velocity as its own circumferential velocity V, and so therefore the Vi is obviously lesser than V is obviously more than F, less than V, or Vf is greater than V is greater than Vi, because there is a change in the thickness of the material, and the change in the thickness is always in the forward direction. So therefore the final velocity of exit of the sheet is the initial velocity plus the velocity at which the metal is getting formulated, and therefore Vf is greater than Vi, and V is obviously somewhere in the center, so V has to be greater than Vi and less than Vf. So the point where the velocity of the strip is equal to the roll velocity, we will refer to that point as the neutral point. Okay, so the point at which the strip velocity is same as V, the roll velocity is the neutral point. So obviously now we will do all our analysis in context of all these different criteria which has been laid down, and I will close this module here, but in the next module we will look at the various forces, the various the pressures which are generated, the power which is consumed at the bearing, etc., in one crisp form by assuming all these simplifications and going ahead with modeling the rolling. So till and until then, goodbye. Thank you so much for being with me.